So in this problem, we're asked to find the area of a region. And there are a bunch of different ways that we could break this region up into pieces, into individual integrals, lots of different ways. It's made complicated by the fact that in this portion right here, we're looking for the area between the two sides of this square root curve. Then, to the right of that, we have a region that is between a line and just the top square root curve. So we could potentially find this integral that way. So let's do that. Let's write that as a couple of separate integrals. So the first thing that we could do is an integral going from -3 to -1 of the top function, which would be the square root of 2x plus 6, minus the bottom function, which is negative square root of 2x plus 6, all of that dx. Okay, so that takes care of the left portion. And then to find the right function, the purple area, we would make that another integral that would go from -1 to 5. Our top function is still the square root of 2x plus 6, but now our bottom function is the function y equals x minus 1. So we're subtracting x minus 1 from that top function of square root of 2x plus 6. Okay, and we would take those two areas and add them together. Now, this is it's not that difficult, but it's just annoying. It's kind of challenging to evaluate all of this. And so you might wonder, is there a better way? And the reality is that there absolutely is. In order to kind of see this better way, though, I'd like you to think about a concept that involves switching axes. So very simple. The idea of the fact that we are used to axes that are written this way. So we have positive y going up, and we have positive x going to the right. I want you to think about, instead of thinking of this more traditional label, I want you to think about this as a possibility, that instead of labeling it this way, let's label this top axis as x and this bottom axis as y. Now, things are going to be inherently different when we start graphing this way. For example, if I wanted to graph y equals x squared, which we know is a parabola, on these axes, the curve would actually look like this. So this would be the positive half of our y equals x squared, because this is positive x and this is positive y, and the other portion of the parabola would be down here. Okay, so nothing too crazy going on there. Let's do this again with another function. And so this time, I'm going to try to graph a function. I'm going to label this the way I showed you. This time, actually, let's put our, let's make this our positive x direction, and let's make this our positive y direction. So as we're doing this, let's graph this in red. Let's say we wanted to graph the line y equals x plus 1, just to throw out an example. Okay? If that was the case, the line y equals x plus 1 has a positive slope. Now, the reason that's relevant is if we were drawing our graph now, so let's put a little scale on here. Here's 1 on the positive x-axis. Here's 1 on positive y. When x is equal to 1, y would be 2. So we have a point there. We have a point at x equals 1. And if we drew a line through those points, it would look like this. Okay, now this line is the line y equals x plus 1 if our axes are defined this way. And you might look at this and say, this is crazy. We know that as x increases, y should increase for a positive slope, but we don't see that on this line because we have labeled the axes differently. Okay, now, the reason I'm suggesting this is that there are some advantages to being able to switch axes that relate to solving problems like the one that I showed you. Let's think about what it would mean if we could redefine these axes in a slightly different way. Specifically, let's say that this axis here, going up, is x, and that this axis over here is positive y. So let's say that you were asked to find the area inside these two curves. Now, before you say, great, now we have to regraph everything, we actually don't. because if we were to solve both of these equations for y, in this equation we would have y equals x minus 1, which is what we have above. And if we were to solve the other one, we'd get x plus 3 equals 1/2 y squared. Multiplying that out, we'd get y squared is 2x plus 6, so y is equal to plus or minus the square root of 2x plus 6. These are the same graphs. Okay? But if we can think about the graphs in this new rotated way, here is why this makes things much easier. Since this is y, and since this is x, we can again use the concept of top function minus bottom function for this region. We're trying to find the area inside all of this. And so we can think about a single strip drawn between these two graphs. So here is a single strip, right, drawn between the two. And this is a small strip. If this is kind of the top, remember, in these rotated axes, and this is the bottom function for this entire region, you notice that for this entire region, there's no switching around. The line is always the top function, and the curve is always the bottom function. So this means that we can find this integral by taking a top function, and that is x equals y plus 1, and subtracting the bottom function, which is 1/2 y squared minus 3. We do all of that. We're integrating, this time not dx, because this change right here is a delta y. So this is going to be integrating with respect to y. Since we're integrating with respect to y, our limits of integration are going to be from y equals -2, that's this value right here, where the region starts, to y equals 4, where the region ends. And so you see now we have a single integral that we can evaluate in order to get this. And this is something that we can evaluate without too much trouble. We can simplify that expression there, and in doing that, we end up with -1/2 y squared plus y plus 4 multiplied by dy. We can find the indefinite integral without too much trouble and evaluate it, and we end up getting, okay? So we went from a very complex region with two separate integrals to find that area to a single integral, all because we were able to switch axes and redefine this as a problem using horizontal strips.